What if I told you that the skyscraper you're looking at right now could actually be a giant battery, not with chemicals or lithium ion cells, but with something as simple as gravity? Yeah, you heard that right. We're talking about lifting heavy stuff up and letting it fall back down to store and generate electricity. Sounds crazy? Well, it's not only possible, it's happening, and it might just revolutionize how our cities store energy. Today, we're diving deep into gravity energy storage in high-rise buildings. We'll break down how it works, why it's brilliant, and what challenges we need to solve to make this the future of urban energy. Let's get into it. So, first things first, what exactly is gravity energy storage, or GES for short? Think back to high school physics. Remember the formula E equals mgh? Energy equals mass times gravity times height? Well, that's literally the entire foundation of this technology. Here's how it works in a building. You take a super heavy block, we're talking tens or even hundreds of tons, and you lift it up inside a vertical shaft in a skyscraper. When you lift it, you're storing energy as gravitational potential energy. Then, when you need that energy back, you let the block descend slowly, and as it comes down, it turns a generator that produces electricity. It's essentially a massive mechanical battery built right into the building's structure. Now you might be wondering, why use a building? Why not just build these systems on the ground? Great question. The answer comes down to three words: urban land efficiency. In cities, land is insanely expensive. Building a ground-based storage facility means buying land, getting permits, dealing with neighborhoods. It's a nightmare. But skyscrapers already have something most buildings don't fully utilize: vertical space. Every high-rise has elevator shafts and service cores, these tall, empty vertical tunnels that run from the basement to the roof. This is basically dead space that doesn't generate revenue. By integrating GES into these shafts, you're turning that unused volume into a commercial energy asset without needing a single extra square foot of land. The energy you can store is determined by three things: the mass of the block, gravity, and the height of the building. Now, gravity is constant, it's always 9.8 meters per second squared, and the height is fixed once the building is built. So, the only thing you can really control is the mass. The heavier the block, the more energy you can store. To maximize energy storage, engineers use what's called high-density concrete. This isn't your regular sidewalk concrete. We're talking about concrete mixed with heavy aggregates like barite, magnetite, or iron ore. Standard concrete has a density of about 2.3 grams per cubic centimeter. High-density concrete? We're looking at 3.5 to 5 grams per cubic centimeter, more than double. Some of these blocks can weigh over 300 pounds per cubic foot. And here's the cool part. These blocks can be made from recycled materials, local waste, composite materials, even industrial byproducts. So not only is this system sustainable from an energy perspective, but it's also circular from a material standpoint. The mechanical systems are actually borrowed from elevator technology. You've got motor generator units, high tensile hoisting ropes, gears, basically the same stuff that moves elevators up and down buildings every day. But here's the key difference. Regular elevators use counterweights to balance the load and minimize the energy needed to lift people. GES systems do the opposite. They're designed to maximize the mass being lifted because more mass equals more energy stored. When you're charging the system, the motor lifts the heavy block. When you're discharging, the block descends and the motor switches to generator mode, producing electricity. It's beautifully simple. Okay, engineering is cool and all, but let's talk money. Does this actually make financial sense? According to recent studies, absolutely. When you combine GES with on-site renewable energy like solar panels on the building facade or rooftop wind turbines, the levelized cost of energy comes out to between 5 and 11 cents per kilowatt hour. That's highly competitive with pretty much every other storage technology out there. And get this, the payback period ranges from 9 to 17 years undiscounted and below 25 years when you factor in discount rates. Considering these systems can last 30 years or more without degrading, unlike batteries that lose capacity over time, that's a really attractive investment. With GES, you're not just storing energy for yourself. You can provide multiple services simultaneously. Inside the building, You're doing peak shaving, storing cheap electricity at night, and using it during expensive peak hours. You're also making the building resilient against grid outages. Outside the building, you can sell services back to the grid, things like frequency regulation, voltage support, capacity credits, basically helping stabilize the electrical grid. And the grid operators pay good money for these services. So you're generating revenue from multiple sources at once, which dramatically improves the return on investment. The most successful model is what's called a hybrid renewable energy system, or HRES. Here's how it works. You've got solar panels or wind turbines generating electricity. That power goes into the building, but when you generate more than you need, you store it. The GES handles the bulk, long-duration storage, we're talking 4 to 24 hours or more, and then you pair it with a smaller lithium-ion battery for quick, short-term spikes. This combination gives you the best of both worlds, the longevity and safety of gravity storage with the fast response of batteries. Alright, so this all sounds amazing, but let's be real, there are some serious challenges. First up, structural engineering. When you're moving hundreds of tons up and down a building, you're creating massive forces. We're talking about both static loads, the sheer weight sitting at the top or bottom, and dynamic loads from acceleration and deceleration. Most buildings are designed for static loads, but when you have a moving mass, you need to worry about something called dynamic response. If the speed of the moving block matches the building's natural frequency, you could actually cause the building to resonate, which is obviously not good. So, engineers need to do specialized dynamic load analysis, treating the mass as a moving load on a beam structure to make sure the building can safely handle these forces without compromising structural integrity or making people uncomfortable. Remember how we said we need super high-density materials? Well, there's a catch. While high-density concrete is great, there's a limit to how dense you can make it while keeping costs reasonable. Some recycled materials sound good in theory, but are actually too light, like cenospheres, which are fly ash byproducts with a density of only 0.4 grams per cubic centimeter. That's way too light for our purposes. So there's ongoing research into finding the sweet spot. Materials that are dense, sustainable, cost-effective, and available locally. And here's another challenge. Can you add this to existing buildings? Maybe. It depends on two things: available space and structural capacity. Older buildings might not have shaft spaces that are big enough or properly shaped. More critically, buildings designed before modern seismic and wind standards might not have the structural strength to handle these massive moving loads. You'd need extensive structural analysis before attempting any retrofit, and in many cases, it might just not be feasible. Let's zoom out and talk about the bigger picture. Buildings account for about 30% of global energy consumption and greenhouse gas emissions. That's enormous. If we can turn high-rises from passive energy consumers into active energy assets, storing solar and wind power, reducing peak demand, stabilizing the grid, we can make a massive dent in urban carbon emissions. This is about decarbonizing the built environment at scale. So, what needs to happen for this to take off? 3 things. First, we need standardized dynamic load analysis methods so engineers can confidently design these systems. Second, we need new building codes specifically for mechanical energy storage, focusing on reliability and structural safety rather than fire prevention. And third, we need policies that incentivize value stacking, allowing buildings to provide both internal energy management and external grid services, creating multiple revenue streams. Look, gravity energy storage in skyscrapers isn't science fiction. It's engineering reality. The physics works, the economics work, and the technology exists. We're basically turning every high-rise into a battery that lasts 30+ years, doesn't degrade, can't catch fire, and helps stabilize the grid while cutting carbon emissions. The real barriers aren't technical, they're regulatory and institutional. But as cities around the world push for carbon neutrality and energy resilience, those barriers are starting to crumble. The future of urban energy might just be falling up. Thanks for watching. If you found this fascinating, hit that like button and subscribe for more deep dives into cutting-edge technology. Drop a comment below